All right, I think this is gonna be the last video for chapter 5. I do have several examples in the notes. Not very many. This is actually a pretty long activity, the birthday problem. We'll maybe do it in class if people are interested and if we have time. But let's maybe just do these last two examples. I think this is a good example of a question that's kind of difficult and might trip people up on an assessment. So they give me the probability of A, they give me a probability of A or B, right? That's an or. And they ask me to find the probability of B if A and B are mutually exclusive. So I think some kids might get kind of stuck. It's like there's no context, I can't do anything intuitively, where do I go from here? But think about the definition of mutually exclusive. If two events are mutually exclusive, then the probability that A and B happen together at the same time is 0. So I know A, I want B, and I know the or, and I know the and. So what equation on your formula sheet relates all those things? The additional. The probability of A or B is the probability that A happens. Start my calculator up here so it's ready to go when I need it. Times plus the probability that B happens minus the probability that A and B occur. So I think I have everything except the one thing I need. Or, that's 0.6. A, 0.4. B, that's my unknown. And then probability that A and B occur is 0. So basically, just subtract that 0.4 from both sides, and you get the probability of B. Oops. Okay. All right. Second part. Again, find the probability of B, but this time not if they're mutually exclusive, but if A and B are independent. Okay. Yeah, this is kind of a tricky one. I think we're actually going to use the same formula, or I can use the same formula. It's just now this isn't necessarily equal to 0. But what is it equal to? Well, let me write it down. So the probability of A and B. So here's the thing. If these events are mutually exclusive, then the probability that A and B occur is simply the probability that A occurs times the probability that B occurs. When you have independent events, you just multiply their probabilities together. So let's plug our stuff in again. 0.6, 0.4, this is unknown, minus the probability that A happens is 0.4, and this is still unknown. So we can kind of just treat this thing like a little variable here and solve for it. So let's move this over. That gives me 0.2. What is one of these minus 0.4 of these? That would be 0.6 of those. Divide both sides by 0.6. Probability of B occurring is 0.2 divided by 0.6, which I think is 1/3. So those are two problems where you need to use a formula, and it might not be real. I mean, you can say, oh, well, you just subtract those to get this one. Yeah, but how do you know you subtract and you don't add and you don't multiply and you don't divide? That's where the formulas kind of can help us, or we don't have intuition to fill in the gaps. Example, poker face. Oftentimes I don't do these examples because I know some kids don't know much about cards. You will never see a question about cards on a test unless I tell you, you got 6 black cards and 3 red cards. So you'll never have to know all the suits and all the colors and all the stuff about cards. But I am going to do this one example, and it's just basically talking about clubs and talking about colors. So in a regular deck of cards, 52 cards, you have 13 red. Nope. You have 26 red and 26 black. And then of those 26 black ones, you have 13 clubs, 13 spades. The red ones, you have 13 diamonds. and 13 hearts. Okay, so that's kind of the breakdown that you need to know on this one. So the first card is a club, the second card is red. So what's the probability that the first card is a club? Well, there's 13 clubs out of a total of 52 cards. You know, I don't really want to reduce all of these, but I guess I probably should because I expect you guys to. It's going to be 1/4 because there's 4 suits, so 1/4. Probability the second card is red. Again, this is the one that confuses kids. I like to discuss it in class. What's the probability the second card is red? Well, it doesn't matter what the first card is, right? Probability the second card is red, if you don't know what the first card is 1 out of 2, or 26 out of 52, or 1/2. Another way to think of it is, what's the probability that if you cut the deck in the middle here, what's the probability that where you cut it is red? And most people would say that that's 1/2. And I'd say, well, what is it? But what about the 20 cards that you cut above it? And you're like, well, it doesn't matter. I don't know what those are. And that's the exact same thing. You draw the cards off. You don't look at them. So just take off 20. What's the probability that that 21st card is red? Well, that's 1/2. It's the same as the second card, same as the first card, same as any other card. It's the knowing of the first card that changes the probability of that happening. Anyway, so what's the probability that the second card is red given that the first card is a club? Now this changes because now you know what happens on that first card. So if the first card is a club, that means you got 1 less card and 1 less black card. That means, but you still have the 26 red. However, now it's out of 51. And that probably doesn't reduce. So just leave it. We could talk about percentages here. Let's do it as a decimal here. 509, 5.1, 0.51, or this was 0.50. So this is an illustration of lack of independence. If you take that first card and look at it and put it off to the side and then draw the second card, it changes slightly the probability that that second card is red. Find the probability that this is B and A. So what's the probability that the second card is red and the first card is a club? I don't know why I reversed this, but that's also A and B. It doesn't really matter. It's symmetric. So the probability of the first card is a club. Well, the probability of the first card is a club is 13 out of 52 times, and the second card is red. So this is the probability the second card is red given the first card was a club. So that would be the 26 out of 51. This is 1/4. I didn't. So just type in my calculator, sorry. 13 times 26 divided by 52. Dope. 13 times 26. Gosh, what's going on? You guys are like, you're wasting my time with this video is what's going on. Sorry. Control Enter. 127. And what's the probability that you get A or B? So this is the probability that the first card is a club or the second card is a red. So, part of me wants to try to do this intuitively, but it's not really clicking with me intuitively. The first card could be a club and the second card could be anything, or it could be a red, or the second card could be a red and the first card could be a club, or it could be anything also. So whenever you start getting confused, it's just, why try to do it? Don't hurt your little brain. Use the formula. This is the addition rule. I think I have all these things already calculated. Probability of A is 1/4 plus probability of B is 1/2. That's B, regardless of what happened on that first card. So that should be this one. Minus the probability that they both happen. Well, I just calculated that. That's 0.127. So 1/4 plus a half minus that last answer. So 0.25 plus 0.5 minus my last answer gives me 623. 0.623. So there is a 62% chance that the first card would be a club or the second card would be a red. So notice we kind of hop between intuition and the formulas. You know, kind of do whatever's easiest for us. The birthday problem. In a class of 30 kids, 2 students were surprised to find out that they had exactly the same birthday. Find the probability that at least 2 kids in the class have their birthday on exactly the same day. First, estimate it intuitively. The reason I ask you to do this is because I think you're going to find that the probability is actually a little bit higher than you might think, and maybe even quite a bit higher than you might think. And then let's run a simulation. We would do that in class, and then let's calculate by hand. We may do that in class, we may not. It's a bit of a involved calculation, but it's not that bad actually. All right, but I'm not going to do this here, so this concludes chapter 5. Good luck preparing for the upcoming test.